Memory a little bit. We talk about grating. And grating is elements very similar to atron. Well, atron is an element like this big. Okay, atron is like this big, and you can specialize on optical coating, so you do optical coating on these two sides. And then this piece of element could resolve the spectral width of some lasers, for example. Okay. But then grating is totally different. Grating is some structure like this, and then you send light through it. Once you send light through it, then you see that along some directions you get diffraction orders. Okay, so this is okay. So this is a grating diffraction. Along some directions, you see constructed interference, and this constructed interference, of course, depends on the wavelength. So we can use this piece of the element to measure the wavelength of this laser. Okay. If I send the light along some direction, for example, you see the separation of the dots change. If I do a normal instance, it's going to be like this. And then if I do a angle instance, you see the separation change. So the diffraction order depends on the instant angle right here. Okay. And those are parameters that you can play with to measure the wavelength. And if I change the wavelength to red light, then you see the spacing also change. It's not so bright. Perhaps here, you see some faint dots next to the central spot, right? But the separation between two dots also changes with the instant wavelength. So this means that you can have a useful instrument built upon this, and then you can measure the wavelength or try to characterize the light source. Okay. But apparently, if I want to see the separation clearly, for example, if I do this, you see the separation clearly. But if I make my instrument really small, like this, wow, then you need to build everything more compact, try to resolve the two dots. So it's easier that you do experiment over longer distance, and then you can just measure the separation of the dots. So it turns out that the grating spectrometer is relevant. The resolution of the grating spectrometer is relevant to the size of the instrument. Reasonable, right? If I have a big room, then you can see clearly the separation of the two dots. But if I build everything very, very slowly, like this table, and then I'll be working with this. Wow, I need to precisely measure everything within a small distance. Then it's more difficult, right? So a grating monochromator, the resolution of the grating monochromator is going to be relevant to the size of the monochromator. So if I want to build something that can resolve the wavelength in a very compact location, then some people just use a piece of atron. And the physics are almost the same. I told you on last Wednesday, the physics are almost the same. Okay. So we went through this. We calculate this, the free spectral range, right? And if I send a laser along this direction, you see some diffraction, constructed spots along this direction. But if you change the wavelength or frequency here, then along the same direction, you can see a signal, even though you change the frequency to some other value. And the difference between these two frequencies will give you a free spectral range. Okay. So this is how you do the calculation. We did it last week. And then we determined that the finesse of the free spectral range, that is this range divided by this width. This tells you some information about the resolution, right? So you end up having a free spatial range given by this expression. And then we also know the separation of these two peaks is the integer multiple of pi for the alpha interference phase. Then you end up having finesse equal to n. Okay. When I say the finesse equal to n, what is n? Christian, do you remember what is n?
The order?
No, it's the number of grating grooves. For a piece of grating, it looks like this, and there's a certain width associated with it, right? And there's a certain period associated with it. And then if you multiply A n, this is going to give you width of grating. So this is number of groups on a piece of grating. Okay. So this n determines the resolution of this, the spatial resolution of these elements. If you have big n, then you can resolve this pretty well. Okay. If this is very narrow, this means that the wavelength selectivity of this grating is very good. Remember that well, when you see a dot, there's a certain width associated with it. The width in the angular space is going to be given by this for spatial width, spatial width. Right? Now, within this angle, then you see a bright spot. Okay, and this is determined by n. And this n, so this means that well, if you have a piece of grating like this, you send your light onto this. And even though you send your laser onto this, but your laser spot size only cover a small portion of it. That's not good. So you want to cover the whole grating to get resolution. So when you do experiment, you want to cover the whole grating to get full n. Okay. So this is a very practical experimental skill. When you do this, there's no resolution. There's no resolution because my laser spot size is just this big, but my grating is this big. So you want to expand your beam to cover the whole grating. This will see laser, and this will also see laser, this will also see laser. Then you get full interference. Those are like the antenna array. Okay. You want all the antennas to radiate to do interference. Right. So this is finesse. And then we also talk about chromatic resolving power. Chromatic resolving power is that the numerator is the frequency of the laser. And here the denominator is the width in this diagram. Okay. For finesse, the numerator is this. The denominator is this. But for chromatic resolving power, the numerator basically is the frequency of the laser. Okay. So for this particular case, what is the numerator? 分子是什么？是这个雷射的频率。Okay, so given this, if you do f divided by this, you get a width for this diagram. If you are interested in knowing the width of this, because the width of this gives you some uncertainty in your measurement. Okay. Ideally, you want this to be a delta function. Then, if I have a delta function in this diffraction pattern, if I have a delta function, it means that I just walk here, and then there's a very specific spot I can measure. If there's a certain width here, it means uncertainty, right? If I use this if I use this as an instrument, ideally I want this dot to have no size. If this dot has some size, this means there's an uncertainty. Sure, can you get your point? Right? If I send a laser like this, and then through the spacing, I can determine the wavelength of this laser. Agree? By using my grating formula. Can you catch it? Right? If I want to measure the wavelength of this, and then I say through this, hey, through the spacing, I can calculate the wavelength of this guy. Agree? But then, if I have a spot size, this big, well, I run into some difficulty to determine the location of this spot. Right? He said that, hey, that's just a measure of center location. But it still means that you need to be able to determine the center of this spot. But then if I have just one dot like this, well, it's much easier. I know that the location of this the interference dot is right here. I don't need to struggle that I have to determine this location. Okay. So this width determines the resolution of your instrument. Very important. Okay. And then how do you determine this width? Well, if you know the free space, if you know the finesse of your grating, you can determine this width. Because you have a tool, the finesse of this grating is equal to the number of grooves. So you just count it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have n. If we know n, and now we know free space range, then you determine this. Additionally, if you know the chromatic resolving power, and you already know the wavelength you want to measure, then the frequency of the laser divided by this width gives you chromatic resolving power, and then you have also a tool for doing calculation. This m is the diffraction order. N is the number of grooves on grating. Okay, and this is something that today you're going to go through one quiz to do this calculation. Okay, so make sure that you understand the concept. All right. So specifically, let's build a spectrometer like this. If we use the litho grating, what do I mean by litho grating? This is a zero order beam. Instant angle equal to the refracting angle. Well, if I have like a sine theta m minus theta I equal to m lambda. Good job, could you just not control, please? Okay. Well, look at this. If we set this m equal to 0, for the zero order beam, theta diffraction angle is going to be equal to instant angle. Okay. So this is the zero order beam, just like you send the light onto some reflection surface. Okay, if you send the light onto some reflection surface, then you see, once you send the laser, you see a reflected light here, satisfying this condition. Okay, this is just a smooth surface. But then you have diffraction orders. You send the lights onto this direction, and this is surface normal, and then this is zero order beam. And because of constructed interference along some directions, you start to have other diffraction orders. For example, this can be m equal to -1, this m equal to 1. Okay, just like when I did this experiment for you, Where is my grating? Right here. Look at this. You see different diffraction orders. Okay, and this is transmission grating. Well, I can also do diffraction grating experiment for you. Oh, this is the refraction grating. Right, I send my light along this direction and it gets reflected. Can you identify which one is the zero order beam? The centermost one. You can point out where it is, right? Could you just walk over and then point to people? Which one is zero order beam? Yes, which one is minus order beam? Not quite. On the other side, yes, that is minus order beam. That is closer to the surface normal. Okay. And the other one is m equal to 1 beam. Which one is it? And m equal to 2? Yes, the small dot. That is m equal to 2. And m equal to minus 3. Which one is m minus 3? Yes, that is minus 3. All right, so you fully understand it. Wonderful, thank you. He is an outstanding teaching assistant. Okay, so everybody catch it, right? So this is diffraction orders. And the whole thing follow this formula. So be careful about the definition, the sign of theta I, theta n. Okay, theta I is positive. But then on the other side, theta n is positive. So be careful that when theta m is negative, then theta m is on the same side as the theta I. Okay, for example, this surface normal direction is like this, right? So along the zero order beam, if the theta I and theta m are on the same side, with a reference to the zero order beam. If theta I and theta n are on the same side, then theta n is going to be a negative number. Theta n is positive if theta n is on the other side of the zero order beam. Okay. So this is the surface normal, and then your instant beam is like this, and then you have theta I. Okay, and this is the zero order beam. On this side, you have theta n, that is positive number. On this side, you have theta n, that is negative number. Okay, so this is the literal configuration. If your instant beam, the direction coming down from the instant beam is the same as diffracted beam. So this will be m equal to minus 1 because the zero order beam is right here. So on this side, theta m is going to be negative. Okay. So think about that. You have one light coming this direction, zero order beam coming like this, and minus 1 order just trace the incoming direction in the opposite direction, and we call this literal configuration. And this configuration is very easy to construct and very easy to measure. And then we calculated the resolving power for this case. And in fact, this is the consideration you're going to do today in your quiz. Okay, want to know how good you can resolve the wavelengths and so on. All right, so we went through this last Wednesday. So we are in a position to calculate we're in a position to construct some instruments. Okay, but one more point I want to emphasize is that you can see that when this theta I approaching 90 degrees, okay, when this angle approaching 90 degrees, this means that you have grazing instance. Your light is going to go along this direction, very, very close to the surface. And then this value approaching infinite. This means that your resolution can approach infinite. That is wonderful if we design something that has an infinite resolution. then you can resolve the parameter you want to measure with great accuracy. Okay, so you want to have a big R. If you have a big R, relatively this width is going to become a delta function. And we just said that if this is a delta function, you have a big accuracy when you do the measurement. Can you feel that, right? So how do I make this real big? Well, wavelength is sometimes it's not something you can control depending on the light source. Hey, you can make this grating really big. This is the width of the grating. Okay, and this, make it big, then theta I, make this theta I almost 90 degrees. Then you get a bigger resolution. But the difficulty is that if I make the incident angle nearly 90 degrees, you see that the light become weaker and weaker. If I continue to make almost 90 degrees, you see the separation bigger. If I do a large angle diffraction, you see the central three dots are quite bright, right? But if I increase the incident angle, the diffraction efficiency, the intensity become weaker and weaker because diffraction efficiency become poorer. Okay. For example, I'm doing grazing instance right now. You see the dot, the intensity of the dot reduced quite a bit. Zero order beam always the strongest. Okay. But you see that now I'm doing the grazing instance. The intensity of the dot dropped dramatically compared with this small angle instance. So diffraction efficiency is something. There's no free lunch. If you want to have a big resolution, very good resolution, you need to work with the dim light, a weak light. So this is the problem. So smart people in fact invented such an accurate grating. They are able to rule this grating with the slanted surface like this. So if you want to pick up your signal along this direction, let's rule the grating with such a reflection surface. Then you can increase the diffraction efficiency. So this is the engineering, the art of engineering. So engineers are wonderful. You people are engineers. So your ability is to solve real world problems. The physics has been solved by physicists, but then you, as the engineer, you design such a structure to boost up the diffraction efficiency. Okay, so this is the one solution. And today you can buy such an accurate grating in the market. And then how do you construct a literal grating? Well, this is the literal grating. Okay, whenever we did the analysis, we always use a plane wave. We always use a plane wave. How do you pick up the signal within a fixed distance from a plane wave? A plane wave is more like a wave coming down like this. But then if we put lens here, the wave is going to collapse into a spot right at the focal distance for you to do measurements. So when you want to measure something, you need to convert a plane wave to a spot for your measurement. So this is quite intuitive. Stop ruler, could you accept this? Right, a plane wave going through a lens, then it's going to focus into a spot. So this is intuitively correct, right? And in terms of optical terminology, we say that a plane wave basically is a source at infinite. If I have a source right here, then up to this point, you become a plane wave. So basically, a plane wave means that you have an object at infinite. So if you go through this as object plus as image equal to 1 over f, and set this object to be infinite, and Si is going to be equal to the focal point, focal length. So this is the imaging condition. Okay, but in fact, there's a sign convention like this. But I don't want to confuse you. I'll just write plus. Remember this, right, from the first part of this class. All right. So from the optical point of view, in fact, you will be imaging an object at the infinite at the focal point. So this is how you pick up the signal from a plane wave. Same thing, you see a lens right here. You have a source far away, and then going through this grating, then this is plane wave coming down to this grating, and then the diffraction of the grating is governed by this formula, and this formula is a plane wave formula. Shall agree? This comes from a plane wave. Okay, and then if you want to pick up your signal somewhere, put the lens. So you focus the plane wave to a spot somewhere here. Okay, for green light, if this grating angle, the incident angle is correctly, you set this as n, theta n, equal to minus psi, theta I. This is the literal configuration. And then green light will go down to this location if you set this angle correctly. Well, but for different color of light, the diffraction angle will be different. Well, blue light could go to here, red light could go to here. But then you can rotate this, right? You can rotate this. Then you can rotate this into this aperture, so pick up your signal from this aperture. Or just put a linear array, a CCD array right here to pick up location of different wavelengths. And then you can measure the wavelengths based on this formula. If you know incident angle, if you know diffraction angle, if you know the specification of your grating, A, what is A? Sure, you still remember what A is. What is A? Look at this. What is A?
What is the length of one wave?
Yes, the grating period. Okay. Okay, start ruler. A is the grating period. And that is fabricated by you right here, right? In this, it's labeled as B here. This is fabricated by you, so you know this. You know this is the angle, and this is the angle is equal to this angle. Then you can determine this wavelength. Okay, and M is up to your choice. Okay, you can diffract the -1 order beam back or -2 order beam back, up to your choice. For different choice of M, be careful that the resolution different. Right here, the resolution different. Resolving power is different. Okay. For large M, your resolution is better. That is also embedded into this expression. Okay, for large M. So sometimes you want to work with a very thin line to get good resolution. Okay, because when you deal with big M, this means that the diffraction angle is going to be larger when I send this through this grating. Well, you just count the M number for us. For the dim lights here, the diffraction order M will be bigger, right? And at this location, the M is like a ±1. So for large M, you'll be working with the dim lights. But then you have better resolution. All right, so this is the a visual grating parameter is very easy to construct. I used to set up this for undergrad students to do experiment during my tenure in this university. So it's very easy to construct this parameter. Okay. And then, in fact, if you look into the grating diffraction, for different color of light coming in, it's going to go. You start to have some optical path difference between different color of light. Suppose you have a white light coming in, then